Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our third lecture covering material from Chapter 10. The historical gas laws were realized by making measurements on relatively large volumes of gases. The kinetic molecular theory is the best understanding of what is happening to the gases on the molecular level. Listed are 4 conditions that need to be met. The kinetic molecular theory requires an ideal gas, which is not possible because of the interactions in volume that exist with real gases. Gases can behave very close to ideal, though, under the right conditions. These conditions are low pressure and high temperature. This combination minimizes interactions between the gas molecules. And it's also worth a mention that gases with smaller masses tend to be the closest to ideal. If ammonia were released in a room, it would take some time for the ammonia to permeate the air. This delay results from collisions between the ammonia and oxygen and nitrogen molecules in the air, which slows the mixing process. One effect of the many collisions among gas particles is to produce a large range of velocities as the particles collide and exchange kinetic energy. A Boltzmann distribution plot shows the speeds of the molecules within a sample, and it can be seen that a gas at a higher temperature will have a faster average speed of the gas molecules. This is a detailed slide showing the relationship between temperature and velocity of a gas sample at 2 different temperatures. The speed of a gas molecule is inversely related to its molar mass. From the distribution plot, we can see that heavier gases move more slowly on average than lighter gases at the same temperature. 2 vocabulary words that apply to gases are diffusion and effusion, and we have some examples of each. In this visual example of diffusion, you can see that the gas is homogeneous when it occupies the entire container. This is another example of diffusion, and what's really interesting about this image is that you can see evidence of the heavier HCl gas moving slower than the lighter NH3, since the salt is being formed closer to the HCl. Lighter gases will effuse more quickly than heavier gases as well. Graham's law can be used to compare the speed or rates of a gas molecule as a function of their molar masses. This formula can be used for both effusion and diffusion and is typically provided for an exam. Notice how the rate 1 is in the numerator while its molar mass is in the denominator. Most errors when using this formula occur because the molar masses are switched, so be careful. This concludes this lecture and our study of gases for the whole semester. So thanks for watching. Please give the video a thumbs up and subscribe if you'd like to see more mini lectures on the Professor's DuBois channel.